So that was comparing the critical value, our threshold that identifies the rejection region, to our observation in standard error units, which we call the t-score. And our t-score was more extreme than the critical value, so it falls in the rejection region, so we reject the null hypothesis. Another way to do it, and actually the more common way of doing it in the real world, is to use the p-value. This is also a comparison, and we compare the p-value, the probability of seeing what we saw under the assumption of the null hypothesis. So we compare that probability to our significance level. And if our significance, if the p-value is less than the significance level, then it is a significant result, meaning that we reject the null hypothesis. The probability of seeing what we saw is too small, smaller than the significance level, too small under the assumption of the null hypothesis, so we will say, nope, the null hypothesis is probably not right. In this case, the mean is probably not 211. Because the significance level went into creating our critical values, the p-value approach and the critical value approach will always give you the same answer. They do functionally the exact same thing. So you should always get the same answer. Now, of course, they're two different numbers. Critical value is a distance in standard error units, and the p-value is a probability. So the number is not going to be the same. But what you do with the null hypothesis should be the same between the two of those, because functionally they are doing the same thing. So how do we calculate a p-value? We use, of course, an Excel function or a lookup table, but we have been using an Excel function. And the function to use in this particular case is t.dist.2t. It's a t because we are dealing with a t distribution. The dist function, or dist family of functions, means we want to or will be giving Excel a distance, dist, although that's not what it stands for. It does work out that way. We are giving Excel a distance in standard error units, and it will give us a probability, which is what we want, a p-value. So what distance do we need to give it? We give it the t-score. Note that we do not give it the critical value. Critical value is defined only by the significance level. It's defined only by how much probability we want in the tails. The critical value did not care what the mean was. It certainly doesn't care what our data are. The t-score does. So the t-score needed to know whether or not we're dealing with standard deviations and standard errors. And the t-score, hence, is also the distance that we need to move. That is the distance that needs to go into our t.dist function. Because we're doing a two-tailed hypothesis test, we will also put in the .2t. It also makes the syntax, the structure of this function, a little odd. Now we have to give it an absolute value of our t-score. So our t-score is negative. We are far to the left of the mean. This Excel function doesn't know what to do with negative values. So we have to get rid of the negative value. That 2 is still our degrees of freedom. So number of data minus 1. And if we plug all that in, Excel will give us a probability. And in this case, it's a rather small value, about 3%. And so that value tells us, since all probabilities here are areas into the curve, it tells us how much area is still left to the left of our data. And we're effectively saying that if this probability is really small, smaller than the significance level, then it is unlikely to have seen what we've seen. There's only a 3% chance of having observed a sample mean of 167 under the assumption that the true long-term mean was 211. So tiny little part. So we reject, again, the null hypothesis, or again, we reject the null hypothesis. And our conclusion based on the critical value matches our conclusion from the p-value.